Okay, so here we have 1.5 line of best fit, and we have two objectives: to interpret the correlation coefficient for a linear model in context, and to draw a line of best fit given a scatter plot and make predictions. Now here we have a lot going on, okay? For starters, on the left, we have a scatter plot, and those are used to observe relationships between independent and dependent variables, and they often look as if the points are scattered. So you probably know what this is, but I want to hit it again, okay? Because it is super important to understand why we use scatter plots. So if you look here at this scatter plot, you notice that it's very different from a function. The points are scattered. We have to ask ourselves, why are they scattered? And the reason why they're scattered is we're comparing an independent and a dependent variable that may or may not be related. If you think about linear functions, exponential functions, quadratic functions, they all have this perfect pattern and a rate of change, right? But when we look at scatter plots, there could be a relationship, there could not be a relationship. Or, as we like to say it, is there could be causation, or there could be correlation, or neither of those, okay? So let's take a step back. Let's talk about the independent variable. It is your input variable, generally known as x, that is not influenced by other variables, okay? Now that's a tricky one, not influenced by other variables. It doesn't mean that it can't be influenced ever, but is generally something you control and is not influenced by the dependent variable, okay? So here I'm choosing time to school as our independent variable, and time is generally something you will see a lot as your independent variable because it happens. Whether you like it or not, time goes on, right? Now our y variable here would be number of first period tardies, which would be our dependent variable. Now we're assuming here that the dependent variable is influenced by the independent variable. And you know, in this situation, it kind of makes sense, right? Like if the time to school is longer, you probably have more first period tardies, but it's not a guarantee. And that's the huge difference here. We like to think that one causes the other, but that could be completely wrong. And maybe what we really have here is just correlation, that, hey, they're correlated. They're related to each other. There's a relationship there, but it's not a perfect science. Just because I live 40 minutes away maybe doesn't mean I'm going to have more tardies than someone who lives 5 minutes away. Maybe the person who lives 5 minutes away thinks that they can get away with sleeping in because they're so close. And the person who's 40 minutes away, go, I'm 40 minutes away. I need to be more prepared than to get to school on time. So it's not causation. It's most likely correlation for this one. But a scatter plot helps us put this on a graph, and then we could do things like line of best fit and in future lessons, linear regressions, and verify that there's actually a causation or correlation, okay? Or neither. All right, let's talk a little bit about more correlation here, okay? So we have three graphs here. We have a positive correlation, which is this first one. And the reason why we call this a positive correlation is because it's trending positively and we can see correlation. Now, this wouldn't be causation. Causation's, you're going to see like a perfect straight line, like a linear function. That would be causation, right? Correlation is like, hey, they're around each other, they're there, but there's kind of some ebb and flow, and if but they're trending, right? We could see that they're trending positively, so positive correlation, and that's going to have what's called an R value close to 1. So let's take a step back. Let's look at this correlation coefficient, represented by the variable R, a value between -1 and 1 that shows the direction and strength of the values of a scatter plot. What we're basically saying is there's a least squares method that we're not going over right now that helps you find a number from your data that's either between -1 and 1. The closer you are to 1, the more positive correlation you have. The closer you are to -1, the more negative correlation you have. The closer you are to 0 would be no correlation. Okay, so this one obviously is negative again because it's going down. This one's no correlation because it's hard. Like, am I going like this? Am I going down? It's hard to kind of tell what's going on there, so that's no correlation. Now, being at 1 would really be like, would be like a straight line. Being at -1 would be a straight line negatively, okay? So that's why we're saying it's closer, okay? This one on the left here, I would probably say that's like a 0.75 R value. And I would say this one's probably a negative 0.75 R value. Okay, and this one, definitely around 0, but it could have been like a 0.1, right? When the actual least squares calculations are done. But for now, we just want to focus on the type of correlation. So we generally have a couple words for these, okay? We might say that anything like 0.75 and above would be like strong positive correlation, okay? And so then this one would be like a strong negative correlation, okay? Now, let me just draw a little example over here. Okay, if I had something like this and it was just a little bit, a little bit looser, you can see like kind of looks like it's going up, kind of doesn't. We might call this like a weak positive correlation, okay? So a lot of terminology going on here, all right? What's the takeaway here? Okay, focus on the R values. The closer we are to 1, the stronger positive we have. The closer we are to -1, we still have a strong correlation, but it's in the negative direction. And the closer we are to 0, just the no correlation. We have the independent variable and the dependent variable that we are trying to test for a relationship are just not correlated at all. It's just random data, okay? Now, that just kind of made me think of something. I just want to jump back to this scatter plot for a second. We can compare all sorts of stuff, right? Like I could just sit here and go, I wonder if the age of my students is correlated to the number of tardies they have. That could be an interesting question. Maybe younger students have less tardies than older students because they have senioritis. Like there's so many things we could test. And sometimes we're trying to test common sense. Like our common sense would tell us that maybe students with senioritis, get more tardies. But that doesn't mean it happens. Let's get the data. Let's prove that it's there. Let's test if they're correlated. Okay. Now, I want you guys to pause and try this one. All you're doing is estimating the R value for these. So why don't you try and estimate an R value for this, and for this. And I want you to know they're not going to be perfect. We're not doing the actual method right now. We're just focusing on the value. So, best guess. Okay, so for this part here, okay, let me try that again. All right, so hopefully you've given it a try now. Okay, you can see that we know this one is trending downwards. We know we should have a negative, okay? And we're seeing some points that are kind of far off here. Like this one's really far off. For the most part, they're pretty close. I might want to go with like a negative point. That's a tough one. A negative 0.6. Maybe a negative 0.7. I can see making a case for either of those, but this outlier here kind of makes me go more to the 0.6. Now this one is pretty weak, okay? But we can still, because of maybe this pattern right here, there might be something there. I would go with a real low, like a 0.25, okay? Now, a lot of you might gotten closer to 0, but 0 is really we can't even see if it's trending up or down. And if we look at this, we can kind of see that we're starting just a little bit lower and we're ending a little bit higher. There's some sort of positive correlation there, not much. And then finally, this one right here, this is getting pretty good, okay? That's actually really good. You might want to go with like a 0.8, maybe a 0.9. I would want to see much, closer around that. You could even make a case for 0.75 there. I could see that case, but again, we're ballparking. Okay, in this problem, we have Megan and Bryce open a new store called the Donut Pit. Their goal is to reach a profit of $20,000 in their 18th month of business. The table and scatter plot below represent the profit P in thousands of dollars that they made during the first 12 months. So here we have that first 12 months data, okay? And if you look at that, the the profit is kind of going up, but we see some months it goes down, right? Like we made it to 7,000, but then down to 6, and then 7.5, 7, 9, 9, 5, but overall we're going up, and that gives us this data here, okay? Now it says using the line of best fit equation, predict whether they can reach their goal in the 18th month of their business. Okay, now this is exactly why we would use a line of best fit. Okay, we can see we have all this data up to 12 months, everything to the left, but we want to know at this 18th month. Now, of course, this is prediction, right? If we use a line of best fit and we go, boom, it's this much at 18 months, that doesn't mean we'll actually sell that much at 18 months. We need to, see what happens in reality, but we can make a prediction, and based off that prediction, make certain decisions with our business. Okay. Now, we're going to really get into the specifics of drawing a line of best fit here. Okay. If you just go and eyeball it like this, say that was it, and let's carry that all the way to the 18. You can even see its little curve. And then I just go, must be 12,000. Well, look at how difficult it might be to get a slope out of this line, right? Like I see maybe a point here, kind of a point here that looks like a 1/2. Looks like a 1/2, but then I don't really see a good clean. Yeah, now it's kind of jumping. Now this one, yeah, it's like I kind of can get a slope out of that, but I kind of can't, okay? And that's going to make a lot of inconsistencies in your line, okay? Here's what you want to do. You want to try and pick 2 points. Not something you can always do, but you want to try. And I'm thinking, I'm really liking this point with this point. I feel like if I draw a line through those 2 points, it's not the best line. I feel like if I draw a line through those 2 points though, I might have something good there. Okay, yeah, it looks pretty good. All right, my line obviously didn't go through the second point too well, okay, but it's not a bad line. Like look, I got 1, 2, 3, 4 above, 1, 2, 3, 4, 5, 6 below. That's all right, okay. It's not perfect. Maybe I should have used this point, which might have lined up with that one pretty well, okay. Not perfect, all right. You're going to notice that your line is going to look probably very different from mine, and that's okay. Okay, so pretty good line. Let's use our 2 points here to kind of get a slope. So I can see that from here, that went up to 9. So we went from 4 to 9, so 9 minus 4 is a change of 5. And then we went over from 3 to 11, so 11 minus 3 is 8, okay? So that would make our slope 5/8, okay? And it's okay to convert that to a decimal for line of best fit. I think you actually might like it better as a decimal, so let me go 5 divided by 8, so that would be 0.625x, and that's okay, plus 2, all right? You can do either of these. Right? Now, for predicting these values, it might be easier to use decimals with a calculator. Okay? So now we have our line of best fit, and sometimes you're going to see this like little up arrow above the y. That's going to kind of represent that it's, it's an estimation. It's not a perfect line. Okay? So from here we can plug in 18. So I can go y is equal to 0.625 times 18 plus 2. So 18 times 0.625, and we're going to get 11.25 plus 2, which will give us 13.25. Now remember, those answers are in, the thousands, right? So that means that the profit at month 18, would be $13,250. Okay. Now let's go back to our line here. 13.5 would be right here, right? And if you look at this line that we drew, I mean, that's pretty close. Okay, it's a pretty close estimation. All right. And again, reality still has to happen, right? Now, what I want you to do next is I want you to go and try one of your own, okay? And then let's see what happens. Okay, hopefully at this point you gave this problem a try, right? We have a student who waits on tables at a restaurant, recorded the cost of meals, and the tip left by single diners, okay? So we need to kind of label this out, right? We're gonna have to go which one's our independent variable and which one is our dependent variable, okay? So, tip and meal cost, right? Now, the tip is always, like, a good idea is to have it be 15% of the meal cost, right? So you can't have a tip without a meal cost, right? Which would make your tip dependent on your meal cost, okay? So let's put, let's put meal cost at the bottom as our independent. Okay. So meal cost and tip. Okay. Now you may be thinking, well, this question, if the diner orders a meal costing $10.50, how much tip should the waiter expect to receive? I know I just said that generally 15% is ideal, but that's not what everyone tips, right? So this is going to kind of help us figure out what the meal cost and what people tipped, okay? So, we have some interesting numbers: 4.75, 6.84, 12.52, 20.42, 8.97. Let's look at our lowest is 4.75, our highest is 20.42. So we want to, maybe we want to go by fives every two. 20, yeah, okay. And, this is good. It's going to be tough to graph that, all right? Simply because it's going to be hard to graph the number 20.42. We're just going to do our best, all right? And our tip, our lowest is 50 cents. Our highest is $3. So let's do, 0.5, 1, 1.5, 2. Yeah, I messed that up. I need to go down one. See if I can move that. Okay. No. Okay. Let's try this again. Let's go 1, 2, 3, 4. And I know that we won't be using our whole graph, and that's okay. So let's get into plotting here, right? So at 4.75 cost would have been about 50 cents. So that's about a point there. We have 6.84 and 90 cents. So kind of right about there. We have 12.52 and 1.50. We have 20.42 and 3. It's a little bit off to the right, but that's okay. And then 8.97 to kind of bring us back a little bit here, and 1. So 8.97 and 1 is about there. Okay. So here, we have these 2 points, right? We need to draw a line of best fit. I'm gonna take probably using maybe this point right here, so they have a nice solid point. Okay. And I'm gonna use this, but I'm gonna say it's 20 and 3. I'm just gonna go, let me try that again. Nope, curving it. Pretty close, okay? Now we're here, and if I make this kind of, say that this line went through 20.3, not necessarily that green point is 20 and 3, just that it went through it, that would give us 20.3 for a point. We'll say the other one went through, 5 and 0.5, right? So you could, do your subtraction here, right? You can see that we went up 2.5 in the y, so 2.5 in the y, and we went over 15 in the x. Okay. Now here again, 2.5 over 15. Let's just get a nice single decimal out of this. So we use my calculator, and I get a really long, 0.16666 on, forever. Just, I would say maybe round at you could really round at the hundreds because money's not going to go any further than that. So we'll just call that 0.17 x. And if we follow that y-intercept, it looks like it's going down into the negatives, and that's totally fine, okay? So let's say that looks like it might be, negative 0.5, so minus 0.5. All right, now you may be going, well, that's impossible, and you're right, that is impossible, but this is a line of best fit, and we may not even have enough data here to get something perfect yet, and that's okay. All right. So we end up with y equals 0.17x minus 0.5. That's our line of best fit. I'm going to put that right here because estimation. And then I can plug 10.5 into that, right, to see what that would be. So y equals 0.17 times 10.5 minus 0.5. So put that in my calculator. And I end up with a expected tip of $1.28 cents 0.5. So let's round that. Let's make it $1.29. Okay, rounding up there. All right. Now if we go to our graph and we see 10 ends up being at 1.29, that is spot on. Okay, look at that. This would have been 1.5. This would have been 1. We're just, that's a really good, estimation. Okay, it falls right onto that line, and it does look like that's where it should be, right? So hopefully you got something near that, but I really want to remind you guys that you probably got something radically different, and that's totally okay.